Okay, hi everyone. Good afternoon to all. Welcome to our Physics Innovation and Exploration series. Right, today we are really honored to have Yin Yue, right, sharing about her project. Right, she was in the OYPT, which is the online Young Physicist tournament last year. Right, representing Singapore at this international competition. And of course, she's been participating in the SYPT, which is the Singapore version of this competition for the past few years, right? So today we have a couple hours, right? So we can get to understand her project a bit more. And she'll be telling us about something known as the magnetic pendulum, right? But I think sort of the bigger idea around it is the idea of modeling physics as a modeling activity, right? Often when we look around the world, I mean, understanding how things work and so on, is really actually our kind of mental and mathematical models, so that we can make predictions and so on to understand the world around us. Right. So without further ado, in Yue, I will stop my sharing and then you can go ahead and share your slides. And for all participants, I mean, feel free to turn on your camera if you are able to. It just helps a bit with sort of getting it's easier to speak to faces, if that is possible to, that would be much appreciated. Okay, Yue, are you able to share your slides? See.
Yeah, sure. Okay, hi everyone. Thank you, Dr. Tan, for the introduction. My name is Yin Yue. Very happy to meet all of you today, the three of you.
Of course,
Um,
don't worry, we will be recording this and also putting it up so that more people can get to see it eventually.
okay, one moment for the slides. So maybe I'll just give an overview of what we are going to do today. So first of all, I'm going to kind of go through the slides. I think if you went for Minjay's sharing, kind of like what he did, I'm going to go through my slides and basically share a bit more about this problem and how I kind of went about solving it. And then um, I'm going to talk a bit about how we can actually go and model more generic things. And there is a little exercise if you would like to try. Yeah, okay. Can everyone see my screen? Okay, that's great. So hi everyone. This is Euler's pendulum. It was one of the problems in 2023's IYPT. And the name is actually a pun on Euler's disk, which is like a similar system, which is like a similar but not the same system. And this is actually an inversion of the Euler's disk. So it's upside down and it is attached to the plate by the magnetic forces. And this is actually the problem statement. Since we've got a bit more time, I'm just gonna read through it. They asked you to take a thick plate of non-magnetic material and fix a neodymium magnet on top of it. And then you suspend actually a magnetic rod, which they tell you that you can assemble it from cylindrical neodymium magnets underneath it. And then you deflect it and you release it. So I identified several relevant parameters, which I will be talking about later. And they are actually the magnetic field strength of the supporting magnet. So you can think of it as if we have a stronger magnet at the top, it will actually hold the pendulum more strongly to it. The surface of the plate actually the surface of the plate actually affects the damping in the system, and then there's the initial tilt angle and angular velocity of the release. So this is an overview of the slides. And here is actually the experimental setup that I used. It was not the first experimental setup I used, but it was the final one that I used. And what I basically did was to clamp an acrylic board to the lab bench to ensure that it does not shake, and used it as the non-magnetic plate. Then I took wooden spacers. You can see that these are actually pieces of meter rolls. So hey, you can do physics experiments with a lot of the things that you just have lying around. I do not know whether you have meter rules, chunks of meter rules lying around, but yes. Of uniform thickness, they actually use to fix the distance from the supporting magnet, which I affixed with a small amount of double-sided tape so that it doesn't move around. And this is how I actually tracked the evolution of the pendulum. You can observe that the pendulum actually makes an elliptical projection onto the ground plane when it is tilted. So the major axis of the ellipse is actually undistorted and equal to the diameter of the pendulum. And while the length of the minor axis actually changes as a function of the tilt angle. And we can use this to help us track the pendulum's motion. So when we foam umbrella, we can fit an ellipse to the bottom of the pendulum. And when we enforce it, the major axis is actually equal to the diameter. We can use the following geometric relations and accurately determine the position and tilt of the pendulum. Now, I would like to move on to some preliminary observations of the system. So here at the left, you can see if I release the pendulum with no initial angular velocity, it will actually rock. But if we impart a tangential angular velocity, you can think of it as kind of tossing the pendulum a bit, it will kind of roll on its edge instead and track a petal-like pathway. So that's kind of cool. And what I'm going to do next is I'm going to try and qualitatively explain this before we start with the modeling.
Yeah, so in Yue, just to check,
Yeah.
you are saying basically from this slide and the slide before, right? That you are putting the video camera basically directly below the attachment point. Is that how you're doing the video tracking?
Yes.
Okay, so when the video sort of looks at the pendulum, you always see at the edge you have some kind of ellipse because it's a circle seen from the side, lah, right? And that's how you
Yes.
accurately figure out where's the center of that circle or ellipse in that case. Right, great, thanks.
Okay, so one of the key differences, other than the fact that it's upside down, between the eyeless pendulum and the eyeless disc is there's a magnet. So what does the magnet do? Well, the supporting magnet, which is this neodymium button magnet, it actually creates a non-uniform magnetic field. It looks something like this. And the rod is actually axially magnetized. So there is a misalignment of the magnetic moment with external fields. This is not the position that it wants to be in the most, which creates a magnetic torque and turns the pendulum towards the vertical position, which is where it wants to be the most. And this is also additionally interesting in terms of modeling because when you have a magnetic force, there are going to be nonlinearities brought about by these magnetic fields. And as for the interesting motions, you saw just now that we had a petal-like kind of motion. And it looks something like this. I think you can kind of see. I don't know. The GIF is not really okay. So if we actually decompose the motion into Dr. Tan, I think someone is in the meeting room. Yeah, so if you actually decompose the motion into the contact angle oscillations, which is this one, which is where it's moving up and down. Let's go back and do it. Into the contact angle oscillations and the rotation of the pendulum, we can actually see that as long as the periods of phi, which is the rotation of the pendulum, and theta are not integer multiples of each other, the same combination will actually not repeat, and this explains why it looks like a petal instead of an ellipse, or in the limiting case, a circle when the contact angle does not oscillate. But why does the contact angle oscillate, you might ask? And this actually originates due to an initial mismatch of the tilt angle and the angular velocity. There is an initial angular velocity for every tilt angle that would actually perfectly balance it. And this is because when the pendulum actually rotates at a faster speed, there is more centrifugal torque generated, and this would counteract the weight and magnetic torque that wants it to go down. So there's a angular velocity, I think you would agree, for every tilt angle that perfectly would balance it so that there is no net torque on it. And this will actually cause the pendulum to execute circular motion. But however, usually we cannot release at exactly that particular angle and that particular angular velocity. Especially if you do it by hand. So if we release imperfectly with either too little or too much angular velocity, a higher centrifugal torque might actually result in the case of having too much angular velocity, and this leads to a lifting net torque, increasing the tilt angle. And this actually increases the misalignment of the pendulum with the magnetic field and lifts the center of mass. So if you look at it from a conversion of energy perspective, all these describes a conversion from the kinetic energy of the pendulum to its potential energy. And by conservation, the kinetic energy cannot remain constant and has to decrease. Hence, the angular velocity decreases, lowering the centrifugal torque and causing the pendulum to now execute a downswing. This finally decreases the two potential energies, converts it back to kinetic energy, and this cycle actually restarts. And what we get in the end is periodic oscillations of the contact angle. Now, moving on to a quantitative model, now that we kind of have a better idea of why this happens, how can we then model it? We can begin by writing out the geometry. So there is two translational degrees of freedom of the point of contact. You can think of it as the x and the y of this point that is touching the plate. And three rotational degrees of freedom, which would be the three Euler angles of the pendulum. And these are the constants. And these are, we will be working with an inertial lap frame. So the three axes in the different colors are the frame in question, and a rotating frame R, which rotates with the pendulum, and the pendulum's own frame. To model the phenomenon, I actually made use of the Lagrange function, which is defined as such. And from here, we can take partial derivatives with respect to each degree of freedom. And this actually gives us the system of equations of motion. And after we account for the dissipative forces, we can actually solve numerically for the time evolution of the system. So this is one way that you can, oh yes, Dr. Tan.
Yeah, I just wanted to chime in here, just to give a sense for sort of what this Lagrangian method is about. I mean, it's of course more advanced physics, but actually the Lagrangian method is actually one way of sort of doing mechanics problems, similar to what Newton's law does, right? Meaning to say you should get the same result. It's just that it's more convenient in a lot of situations to write this Lagrangian function. It's sort of like in A-level physics, right? You have you look at you actually your objective is actually to study motion, right? You can draw your free body diagram, consider forces on the object, and so on. And then typically you apply Newton's second law, and you get your acceleration out of it, and so on. The Lagrangian method is a bit more like the energy method, in the sense that this Lagrangian function, as she has shown here, L equals T minus V, is actually the difference between the sort of kinetic and potential energy terms, right? And it turns out if because force is also sort of related to there's some sort of calculus going on there, right? It turns out if you Euler and Lagrange, of course, are also mathematicians and so on. If you take some derivatives, right, it can be shown that you actually get your equations of motion, which is equivalently your sort of Newton's laws coming out of it if you take certain derivatives and set up some equations. So the advantage of this method is really you get a very good insight into more complicated kinds of motion, especially when there are certain constraints and so on that happen. So that's how, I mean, you can at this level you can think of it as a sort of mathematical trick, right? But essentially, if you set up your problem properly, actually you start with the physics, you go through the math, and then later on, when you come to the results, you can try to interpret the physics again. Okay, just
Thank you,
wanted to
Dr. Tan.
interject.
I think one way you can think of it is it's not the full picture, but it is a preliminary picture that really helped me when I was in I think year 4 trying to actually do this problem. I think one way you can actually think of it is the potential energy is can give is the potential energy is a function of the position of the object, right? So when you actually take the when you actually do this derivative over here, you can actually get the force term of from the potential energy. And whereas the kinetic energy, it's a function of the velocity of the object, right? So actually this side of the equation, it will give you the MA part of the equation. So this is how you actually end up with the equivalent term of F equals to MA. So yeah,
Yeah, that's very
okay.
nice. Yeah, it's true, right? If you, I mean, in physics, in A-level physics, there is that one of the learning outcomes, right, which says, F equals to minus du dx. Basically, when you take the spatial derivative of the potential energy, you actually get some kind of force, just like gravitational fields. You can actually get your gravitational force from the gravitational potential term, right? And then as in US says, you differentiate velocity, get acceleration. So in that sense, you do get something very similar to Newton's laws, even though it looks more complicated eventually. Yeah.
Okay, so for this system in particular, the angular velocity of the pendulum can actually be written first in its frame, considering the tilt and the rotation and the spin of the pendulum along its principal axis. Then if we write the moment of inertia of a finite rod, we can get its kinetic energy of its rotation about its center of mass. So this is not the full kinetic energy because the pendulum is not just rotating about its own center of mass. If my pendulum is rotating about its own center of mass, you can think of it as such a motion, but it's not rotating about its center of mass. It's actually also, the center of mass is actually also moving. So then we need to consider the motion of the center of mass in the x, y, and z direction, which allows us to write the r vector and the translational kinetic energy. This gives us the total kinetic energy of the system. And here we have the gravitational potential energy and the magnetic potential energy, which is basically the work done to move the magnetic rod in its external magnetic field. Okay. The slide is a bit wonky, but yeah, in this case, the external magnetic field is produced by the supporting magnet. So it's not the moving magnet. This guy is producing the external fields. Now, to find this magnetic field, we can model the permanent magnet as a current cylinder, which is a trick you might see kind of a lot in IYPT reports, I think, if you watch. And what you do is actually you make use of the Biot-Savart law, which is basically just an equation that describes the magnetic field generated by a constant electric current. Actually, we're not saying that the magnet has a constant electric current, of course, but what we are basically saying is we can find the equivalent current cylinder which has which produces the same magnetic field as the permanent magnet, and then we model the permanent magnet's fields by modeling the equivalent current cylinder. So that's a neat trick that you can make use of to model a permanent magnet. Yeah, but to do that, we actually need to find this value, which is Ni, or the magnetization of the permanent magnet, which is equivalent to the surface current density in our equivalent current cylinder. And this is actually, we actually need to characterize it. So how we can actually do it is we can measure the magnetic field of the permanent magnet along its axis. And this actually has a very neat closed form expression. And once we fit for the value of m using this expression, we can find the magnetization, which in this case is this value. Oh yes, Dr. Tan.
Okay, so another interjection. I think this is a good place where I can try to link it a bit more to maybe what you have studied in A-level physics. So I think what Yin Yue was saying about currents, maybe if you think about solenoids, I think the simple example you might know is a solenoid, right? If you have a solenoid with the wires quite round, you do know that when you pass a current through these coils, you get an axial magnetic field, right? You use your right hand grip rule or whatever rule you have, right? Your B field will then sort of be in along your thumb when your fingers are in the direction of the current. Right? So what Yin Yue had mentioned was you sort of model it in that sense. We know that a permanent magnet like this neodymium magnet stack of neodymium magnets, they have a strong magnetic field, right? And of course they don't have any current because you're not putting any batteries or so on. But in the physics of it, I mean it uh we do know that a sort of circulating current can give rise to a magnetic field. And now we're sort of trying to work backwards. If there was a magnetic field, right, what is the current that would be needed for this? And then this graph that she's shown here is really the result of putting a magnetometer or some kind of sensor to figure out the magnetic field strength, right, at various distances along the z direction of the graph of the illustration that she has in the bottom right, right? So you put your sensor at different distances away from the stack of magnets. You measure how many Teslas you're getting on your magnetic sensor, and then you plot it, and as she's shown, right, it fits very nicely with a theoretical model given some value of the current and magnetization for this magnet.
Okay, thank you, Dr. Tan. Okay, moving on. Sorry, one moment. Now the magnetic rod, it is axially magnetized, right? The bottom magnets, they are axially magnetized. So we can solve for the magnetic potential energy of each infinitesimal unit within the axially magnetized rod, and actually integrate this over the entire rod to find the total magnetic potential energy that the rod has at each point in space. And this actually allows us to find the total potential energy of the system. I think another common way that people would model a magnet system is to consider the Lorentz force on the current cylinder. And I would just like to point out at this juncture that you actually get equivalent results if you do that, because okay. So if you put everything together, this is the final Lagrangian expression that you would get. And here is the final system of equations that we can then solve. There are three torque equations, one for each of the Euler angles, and there is a force equation for the motion of the contact point. So the static friction, we can characterize it by tilting the plates that we have set the system up on until the magnet begins to slip, and this actually helps us to derive the static friction coefficient from the force balance. And if you roll a magnet which is not slipping down the plate and fits its trajectory with this torque equation, you can actually obtain the rolling friction coefficient. Yeah, okay. And finally, if you want to find the air drag coefficient on the magnet, you can actually let the entire pendulum swing from a string and fit it with the torque equation to characterize the drag coefficient. And you can actually do this with any any mechanical, you can actually use this method of swinging something or from a string to characterize the drag coefficient of any mechanical moving object in most mechanics problems. But one thing you should take note is that the drag coefficient of something swinging this way will not be the same as something swinging this way. And that is a consideration that you should take into account, I guess, when you're trying to find this. So yeah, this can be used not just for a pendulum, it can be used for a ball, I think this year there was a problem on a rigid ramp walker. You can do that. I think someone did that, I'm not sure. But yeah. Then if we actually have the magnet slip down the slope at a large angle, then we can also use this expression for this expression of F equals to ma to find the kinetic friction coefficient. Finally, to characterize, oh yes, stop the time.
Yeah, so actually I'm quite curious. I can imagine certainly the static friction one, that's something quite easily done. You just you just have some kind of incline where you are able to measure the angle, and then you just vary it to find when it starts to slip, and then the angle is basically the data that you need to figure out what your static friction coefficient is. But for the other cases of rolling and this kinetic friction, you really do have to take a video of it, right? And sort of use maybe some video tracking to work out the acceleration. Is that what you have to do, sort of?
Oh, yeah, definitely. So just to break this down a bit more. So this side is I alpha. This is the moment of inertia times the angular acceleration, and this side of the expression is actually the torque. So what is providing the force that is providing the torque is the net force that is providing the torque at the contact for it to turn at the contact point is actually the static friction minus the rolling friction, which is opposing this. The static friction makes the thing turn, right? So the rolling friction opposes the turning, right? And so this is the force, and this is the wait, I forgot what it was called. Oh my gosh. This is the r. This is the radius of the rotation. Yeah. So and x would be the position. So from this from the trajectory, you can actually find x and find this and then find the second time derivative of x, and this will allow you to actually fit for the value of mu r. Yeah.
Right. So the graph shown here basically is the position against time, something like that.
Yes. Oh my gosh, I'm so sorry. The axis.
I know
Yes.
it probably got cropped off because you were zooming in or something. No worries. And then okay, maybe you'll probably mention it later on, but I just thought maybe if you go back one slide, I will point out something okay, the slide with your Lagrangian your equations of motion. You had it maybe 1 or 2 slides ago. I can't remember
This
how
one?
many.
This one.
Yes. So you see, she has added things in red, right? And sort of it's yeah. I mean, we were discussing earlier on about this Euler Lagrange method, where when you take the d dt, when you differentiate with respect to time, you are sort of getting your acceleration term coming out, right? And if you sort of differentiate with respect to the position or so on, you are getting your sort of force term come out. And these Euler Lagrange equations, you always are assuming that these are sort of integrable equations, in the sense that energy is conserved. But in this case, right, we really want to model it very accurately. So as in order to match your actual experimental data, factors like the drag force, the frictional force, and all that all have to come in. And so what happens in these Euler Lagrange equations is that you get your sort of base equation, then you add in sort of as a correction term, right? Your additional torques, your additional forces that are your non-conservative forces, like your forces that are dissipative, and they actually cannot come out from your Euler-Lagrange equations. So you sort of add it on, and then that makes your model more accurate and more aligned to what actually happens in the macroscopic setup, right? Where actually friction, if you go to the microscopic scale, all your intermolecular interactions, they are in some sense, energy is never lost, right? But sort of macroscopically, of course, these are sort of incoherent terms, and therefore you have to sort of add in these sort of dissipative forces to get your model more accurate. Yeah. Okay.
Oh yes,
Thanks,
thank you,
Yin Yue.
Dr. Tan. So just to add on, I think one way you can think of it is the reason why you can't get your non-conservative forces from your energy terms is because if you think about it, the drag force, for example, the air drag, it depends on how fast your thing is moving through space, right? So that doesn't depend on where it is. So it's not going to come out from your potential energy terms. I can be here and I can be here, but how much drag force I am experiencing depends on how I'm moving and not where I am. So that is why it cannot come out from the potential energy terms and why you would have to incorporate it. Yeah. Okay. Okay, so moving on to basically an experimental account. We are going to go through like the effects of some of these parameters, which would affect the motion, as you would see in a moment. So first of all, if we vary actually the magnetic field strength, what we can see is, oh, this is not varying the magnetic field strength. My bad. Okay. So here you can actually see the time evolution of the tilt angle. So remember how we were saying that the contact angle, the tilt angle actually oscillates, and this is the rotation angle. So it is this angle where it is going around. And here we have their time evolution. And one thing you can observe is that after a while, the pendulum will fall into a vertical position. So now when we vary the magnetic field strength and conduct the same experiment with a larger supporting magnet, which would generate a stronger field, assuming the same magnetization, of course, we would find that the time taken for the motion to damp out is actually shorter. In fact, if we do more experiments and plot this time to collapse against the size of the magnet, such a decreasing trend is obtained. And why is this so? It's actually because when we increase the magnetic field strength, we also increase the normal force on the plate, small damping, and it takes a shorter time to dissipate its energy. We can also vary the initial release conditions. This is quite interesting, such as the initial angular velocity imparted on the pendulum rod. So as we previously saw, a rolling motion, so remember the petaloid motion that explained just now, is observed at high angular velocities, where the pendulum oscillates but never becomes vertical until it finally collapses at the end. However, if we release at a very low angular velocity, we can actually get a different type of motion where the pendulum actually becomes vertical and switches to an opposite contact point, i.e. it exhibits rocking motion. So let's talk about the rolling motion first. The rolling motion forms flowery pathways, and the pathways can look very visually different when we change the initial angular velocity, keeping the initial tilt the same. At lower angular velocities, there are actually larger oscillations that give rise to more irregular petal shapes, and the smaller periods leads to more petals being formed. And indeed, if we define the first oscillation amplitude as A naught, we will find that it actually increases when the initial angular velocity is decreased. So it rocks up and down more. So let's talk about that a bit more. Here I have a plot of the oscillation amplitude, so how much it rocks up and down against the initial angle of against the initial angular velocity while keeping the initial angle the same. And initially at a low angular velocity, the pendulum over here, it's rocking. And the first oscillation amplitude is actually constant, taking the pendulum from its initial release angle to the vertical position. But when we further increase the angular velocity, the centrifugal torque generated by its rotating motion actually increases, and this raises the equilibrium tilt and brings the equilibrium position closer to the initial position of the pendulum. So the pendulum actually only does not become vertical and just oscillates about its equilibrium position. And the larger the initial angular velocity, we actually get smaller oscillations because the equilibrium position is closer to the initial position. Yeah. Now now if we release it perfectly at the right angular velocity, we actually get to that point where the centrifugal torque completely balances out the restoring torques, and the pendulum experiences no net torque in the theta direction, and it does not oscillate. It will just execute circular motion at this point. And finally, beyond that, when we further increase the angular velocity, further increasing the centrifugal torque, the equilibrium position is actually above the release angle, and it leads to oscillations again, but this time it will swing upwards. Now, you would also kind of observe a smaller period of oscillations if you have a lower angular velocity. So why is this so? Here I have a plot of the oscillation period against the initial angular velocity. This is the trend. It looks very funny, but I will explain it as we go on. So first of all, during rocking, when the period is initially increasing, as the period initially increases as the equilibrium angle is raised, and we can understand this as due to the pendulum decelerating beyond its equilibrium position, still going down. So the average velocity is lower for the same angle traversed, and the period is actually longer. Afterwards, the period is actually increasing now as the net torque is decreased with the increase of the centrifugal torque. As the pendulum approaches circular motion, there are no oscillations, which is why we get an asymptote here. And then finally, my slides are hanging, but beyond the equilibrium position, despite the increasing net torque, the period actually decreases due to the larger oscillations. Finally, another thing that we can actually vary is the plate surface. So this one is probably a lot more intuitive. To investigate the effect of damping, we can actually conduct the same experiment, but instead of on a piece of plastic plate, we can actually line it with sandpaper, and this actually increases the frictional coefficient. And the pendulum would actually damp out much faster because more energy is dissipated. This is quite intuitive. So this concludes the presentation this concludes my solution to the problem. In conclusion, these are some of the things that I've gone through today. And these are the components of the quantitative discussion. So how we model the magnets and how we model the mechanical system. And these are some of the parameters that I varied. Yep, thank you.
Thanks so much, Yin Yue. Just now, actually, before you went into the different factors, right? There was a slide on the coefficient of restitution. Was that something that you wanted to cover, or that was more like additional info that's more for later?
Oh, my bad. Yeah, so the coefficient of restitution, why is the coefficient of restitution relevant? Because when the pendulum is rocking, it actually swings through the vertical position and it kind of collides with the plate, and this dissipates energy. You can hear a loud bang when it does that, right? So this is why we characterize the coefficient of restitution. Yep.
Okay. So are you saying that S is doing that petaloid motion? The contact point does actually change. That means it's sort of like now right now, for example, in the picture, it's attached to one end of the cylinder, but it actually can turn around and hit the other end. Is that what?
I see. So we're actually talking about but the coefficient of restitution is actually relevant to the rocking motion instead, which is when we don't give it a large enough initial
Okay,
angular
okay.
velocity. So it does this. It pivots back and forth. It's kind of like a swinging simple pendulum.
Right,
But
right,
it's
right.
yeah. So that's when the coefficient of restitution comes in.
Okay, so that's more for the swinging, but the rest of the results you showed just now were more for rotation, right?
Yes.
Okay, right, right. So this is when the omega, the initial omega is zero. For example, I mean, I guess in the language of because most of the plots you were showing, they started. I mean, your theta, your phi dot lah, I suppose, being zero. Okay. Yeah, and it is true that this I mean, coefficient of restitution is really just about, let's say you bounce a basketball, what's the velocity upon impact and the velocity after impact. So that ratio is related to the coefficient of restitution. So a coefficient of 1 would be, a perfect elastic collision, and anything less than that would be, slightly inelastic. And so, of course, with a magnet and acrylic plates, you do get quite a high coefficient of restitution. Okay, great. Thanks so much, Yin Yue. I think that was really, really insightful. I really appreciated that, because it's, going this a lot of interesting physics. At this point, I'd like to open up to the rest of the audience. Anyone has any questions, or any comments, feel free. Maybe you can start with Rupesh. Rupesh, do you have any questions or yeah, comments?
So obviously I have questions about a lot of terms because I haven't learned it yet, but like the basic understanding of the whole the how to how state and what quantities we need to keep in mind, all the conditions, like all the methods I can understand to a basic level. So yeah, the presentation was very clear, um, and yeah, it was a very good presentation. Thank you.
Thanks so much, Rupesh.
Thank you.
And along the way, if you have any questions, feel free to ask. I think it's true. Of course, it's a lot of stuff compressed into, I mean, 40, 50 minutes. It's still a lot of ground that was covered. So yeah, lots of interesting physics. I mean, it's not just, uh, the simple, I mean, unfortunately, in a lot of school physics, right? I mean, we're looking at how does this point mass move, right? Of course, here you don't have a point mass, you have an extended mass. This cylinder, you know, at different points in the cylinder, there are different magnetic field strength that is experiencing. There's different motion and all that. Of course, it helps that the cylinder doesn't break off, right? I mean, even more complicated situation would be if the cylinder was flexible and so on. But yeah, lots of interesting physics here. What about Yiheng? Yiheng, did you have any questions or comments? Oh, okay. Sorry, I don't quite know how to pronounce the name. Guillaume. So yeah, it's probably, is it French? Okay. But he has a question. He or she. For experiments, how do we know what formula or uncertainty to account for? What are the major minor axes? What do we expect in major applications? Okay, wait. I'm trying to understand the question. Okay, how do you know what formula? Okay. I guess that's the probably the easiest part to answer. I will try to say something, and then maybe Yin Yue can add on.
Oh
I
yeah,
suppose
sure.
I suppose you're asking sort of, how do we approach a problem, right? Let's say you see some phenomena, right? In this case, you put a magnet, you put another magnet, and then somehow they move in an interesting fashion. I suppose you always start with the question of how do we describe the motion, right? Because I mean, at least for a case where you're interested in the motion, you definitely want to describe the motion, right? So in this case, we know that that cylinder of magnets is well, it always stays together. It's a rigid body. So with a rigid body, certainly it's not a ball, right? Where it can roll and so on. It's more like a long thing, all right. So I guess naturally you have your axis, and because we are in three-dimensional space, you always I mean the sort of straightforward thing is to consider your Cartesian axis, right? Your x direction, your y direction, and your z direction. But in cases like this, where there is some rotational motion going on, then actually it becomes very natural to sort of describe these three parameters, not in terms of your x, y, and z, but in terms of some angles, right? Because rotation actually is some kind of rotation in different axes, right? And so that's where your spherical or cylindrical coordinates come in, right? And as to the formula, at the end of the day, when you're dealing with the motion and mechanics, it's basically Newton's laws, or in this case, using the Euler-Lagrange equations to model it. Uncertainty, I think, okay, that definitely comes from experiment, right? As as she did all the various experiments, actually, she probably didn't go into all sorts of detail, because every single time you want to characterize something, right? Even something as simple as the coefficient of friction, or even the drag forces, actually that's a whole experiment in itself, right? Where you have to take data and do sorts of fitting. And that's where I guess the uncertainty does come in, right? Where when you repeat your experiment, you find that the results are slightly different, right? That gives you some measure of your uncertainty, right? I think that's what I can say for now. Do you have anything you like to add on?
Yeah, thank you, Dr. Tan, for that explanation. I think for the uncertainty, I think you can think of it. I think in year 5, the first topic we learn is if you take A-level H2 physics, is measurement, and in measurement you will learn about errors and error propagation. And I think if you are in, I don't know, for my school in year 6, we started doing A-level pracs, and one of the questions they always ask is estimate the uncertainty in this quantity that you're measuring, like for example, the length of the rope, the thickness of the wire. And I think your teacher might tell you, oh, so you should report it to 3 times the precision of the instrument. So that is something like that. When you're measuring the position of something, for example, from a tracker, things like the pixelation of the video, or like if your camera isn't, if your object is moving really fast, and your camera can't your camera can't capture at such a high frame rate, then you will also get that blurring kind of thing. I think you would have seen in experiment videos. When you actually slow them down into frame by frame, you'll see that it's actually a blur. You can't really tell where the object is at. That is where I would say the uncertainty in question comes from experimentally. I hope that answers your question. What are the major minor axes? Are you talking about the ellipse? So if you Google the geometry of an ellipse, the major axis is the longer one, and the minor axis is the shorter one. What do we expect in major applications of experiments? This is I think you're asking like what is the point of doing this, maybe like why do we do this kind of experiments? Why do we model this why do we model this system? Like what is it going to do for us? And I mean, I agree, like directly you wouldn't maybe see any real life, like obviously there's no it's not gonna save a life if I can now figure out how my magnetic pendulum will move. But I think one thing is it can be educational to actually do this as an exercise on the mind, but also I think it's the technique that really matters in the end, because you might not be modeling a magnetic pendulum the next time, but you might be modeling any number of systems that in real life which is coupled by magnets, strong magnets. There are a lot of them out there, and you would be using the same ideas, more sophisticated versions definitely, but you'll be using the same ideas to figure out how they move and why they move and how they should move. And I think that is how that is important in real life would definitely be because I mean, in many cases, I mean, you can't do experiments for everything just to see how it would turn out. Like if you are optimizing a process for some industrial application, you will definitely end up needing a model to kind of optimize your system before you start prototyping, or else you will be spending a lot of money, a lot of money. So I guess that is the applications. I agree with you. This project probably doesn't have that much like direct applications. But yeah, does that answer your question?
Yeah, I thought that was a great answer, Yin Yue. I mean, it's true. I mean, in any particular physics problem that we pose, the application might not be so obvious, might not even be really there, but really the skills and the techniques that you use really in a sense, yeah, that's where this young physicist tournament is coming from, right? I guess it's really a stretch. I mean, high school students doing all this kind of like physics research, it's actually not easy, right? Certainly, even for someone like myself, having done a PhD, I mean, to do a modeling activity like this, it just it's really a great achievement. And once you are able to, see how you can uh, uh, sort of solve something that is relatively well posed, then when you get on to real life applications, let's say you are as in some factory, or you are trying to invent a new device and so on. If you do everything by trial and error, that's certainly going to take a long time, and you probably won't succeed unless you have hundreds of years to try it out. But having that ability to model using a pen and paper, okay, maybe using a computer, that's more realistic, because some of these calculations are not easy to do, but a computer can certainly speed up the process and find numerical solutions that are close enough. So that's really well put in here. Thank you so much. I think Yiheng, just now I sort of saw maybe you were able to unmute yourself. Did you have a question or comment? If not, yeah, that was really wonderful. Uh, uh, oh yes, okay. A lot of questions noted down. Some things very Lagrangian methods. Yeah. So I mean Lagrangian, of course, to be fair, in a typical, I hopefully you continue studying physics in university. I mean, it's typically taught at either year one or usually also year two undergraduate physics actually. But yeah, it's certainly something very interesting, right? And hopefully this gives a bit of a flavor of what it's about. I mean, the math can be a bit intimidating, but actually the physics does make a lot of sense, and it's a really powerful tool for modeling complicated systems, like even I don't know. I mean, all kinds of things you can imagine. A ring rolling down. Okay, let me not describe that too much. Okay, but thanks so much. I think with that, we can call this session to a close. Again, thanks so much, Yin Yue. That was really illuminating. And take care, everyone. Right. Hope to see you at the next PIES webinar. The next one is on the 21st of May. Right. That's a Tuesday. Also the same time, right? 3 p.m. And yeah. All the best and take care. Thank you, everyone, and have a good rest of the day. Bye-bye.
Thank you. Thanks, guys.